So one of the really cool things that you can do in ACI is you can turn unicast flooding on or off. And you can do the same thing with broadcast as well. So notice here, I'm looking at unknown unicast. Flooding's turned off. Enabled something called hardware proxy, but you can turn it on if you want. ARP flooding's actually turned on, but typically in ACI, you're going to have it turned off. So what we're going to do now is we're going to do some packet walks. I'm first going to focus on unknown unicast traffic, and we're going to assume that unknown unicast flooding is turned off. So something called hardware proxy, also known as spine proxy, is turned on. So let's say endpoint 1.1 wants to send traffic to endpoint 3.1. They're on the same subnet. So let's say that in the frame, it's destined for endpoint 3.1's MAC address. Leaf 1's going to receive that. And it's going to look in its endpoint table, and it's not going to know where to send it. It doesn't know about endpoint 3.1. So question for you guys, what do you think Leaf 1 will do with the traffic? So it's not going to flood it. So the answer is it's actually going to punt it up to the spine switches. So remember, spine switches should know about all endpoints. So the spine switches should know that endpoint 3.1 is located behind leaf number 2. So leaf 1 is going to send it to the spine switches, but anytime we send traffic over the ACI fabric, remember what has to happen is we have to add the outer header. So I want you to look at the outer VXLAN header here. And for the most part, everything's the same, except there's one difference. So I want you to tell me what that difference is. What you can see here is the Anycast TEP IP is different. That's something that's different that we haven't seen before. The Anycast TEP IP, what it is it's a multicast IP address that's shared across all spines. So all spines are listening on this Anycast TEP IP address. So essentially what's going to happen here is Leaf 1 is going to hash that traffic, hash this encapsulated frame either out link 1 or link 2. So let's say it hashes it out link 2 and sends it to spine 2. Spine 2 is going to receive that traffic on that Anycast TEP IP it's listening on. It's going to look at the VNID. So one of the great things about ACI is it supports multi-tenancy. So essentially, that allows us to have multiple VRFs, multiple bridge domains running on the same ACI fabric. So to make sure the spine switches references the correct bridge domain in this example, it's going to look at the VNID. Once it does that, it looks in its COOP database. And its COOP database will say, hey, this MAC address for endpoint 3.1 is behind leaf 2. So then what would happen is the spine 2 is going to send it to leaf 2. So it sends that outer header in the original frame to leaf 2. And if you notice here, notice the destination IP has changed. So when spine 2 received the encapsulated frame, originally it was destined to its Anycast IP. But since the endpoint resides behind leaf 2, the spine sends it destined to leaf 2's TEP IP. And we route it. Leaf 2 gets that encapsulation, the encapsulated frame. We'll decap it. It will look at the destination MAC address and then send that traffic down to endpoint 3.1. Again, the two endpoints have no idea all this fancy stuff is happening, all this fancy encapsulation. They just send and receive the original unicast frame. Another takeaway is the power of the spines knowing about all endpoints. So because the spines know about all endpoints, we don't have to flood our unknown unicast traffic. So we can also turn flooding on. So we can turn unknown unicast flooding on. And the way it works is to understand how this works, you need to understand something called an F-tag tree in ACI. So an F-tag tree, it stands for forwarding tag tree. And notice the spine. So let's talk about a couple principles of the F-tag tree. Number one, a spine will be the elected root of an F-tag tree. So notice we have the spine, and so the spine's going to build out the tree. And when it builds out the tree, it needs to make sure a couple things happen. Number one, it needs to make sure all switches are part of the tree. So notice all the other leaves and spines are connected to the tree, and that's because we want to be able to flood the traffic. So if we want to flood the traffic, we need to make sure all switches will get a copy. The other thing that we need to make sure of when we build out the tree is it needs to be done in a loop-free topology. We do not want to be looping unknown unicast traffic throughout the ACI fabric. So now that you're familiar with this tree, let's do a packet walk here. So let's say endpoint 1.1 is going to send traffic to endpoint 3.1. Leaf 1 doesn't know where the destination MAC is, and we enabled flooding. So what we're going to do is the leaf is going to send it over the F-tag tree. So we take that original frame and we slap an outer header on it. So I want you again to look at the outer header and what seems different about this outer header compared to the other outer headers. The answer is it's a GIPO multicast TEP IP. And so I'll talk more about this a little bit later on. But the way it works is each bridge domain gets its own multicast address. So we would send this traffic over the bridge domain's multicast address. And we'll talk more about this later. And what we do is we send it over, in this example, F-tag1. The traffic is simply going to be flooded. So all the switches are going to receive a copy of that traffic sent on tree 1. Leaf 2 will act a little bit differently. So leaf 2 is going to decap it. It's going to look at the destination MAC, and it should know about endpoint 3.1 because it's a locally attached endpoint. So leaf 2 should know where destination MAC for 3.1 is. And so it's going to send that frame directly to endpoint 3.1. So kind of big picture here is when we disable unknown unicast flooding, we turn it off, we use a tree to flood the traffic. Flooding's not as efficient as you can see. All switches get a copy, traffic gets flooded across the ACI fabric. We eventually get the frame to the endpoint though. The other takeaway is we send the traffic over the tree with a special multicast address, and I'll talk more about that shortly. So you might be thinking, okay, we see one tree, but what if this spine fails? Can we no longer send multi-destination or unknown unicast traffic over the ACI fabric, or do we have to fail over to the other spine? Is there convergence times? And then the other thing you might be thinking is, well, what about these links? So these links never get used for unknown unicast traffic. So we just looked at one F-tag tree. In ACI, we actually have 16 F-tag trees. Now, 4 of the trees are reserved for ACI control plane traffic. 12 are actually used for data plane, for things like unknown unicast and broadcast and that kind of stuff. So we have 12, and those 12 trees will get split across the spines. So since I have 12 trees, 4 spines, those spines are going to be the root for 3 trees. So notice spine 1 is the root for tree 1, 5, and 9. Spine 3 is the root for F-tag 3, 7, and 11. So you can see here's the F-tag tree for tree 1. Here's the F-tag tree for tree 3. The root is spine 3. So I just wanted to mention how we have 12. And so the benefit of having multiple F-tag trees is we don't have a single point of failure for our multi-destination traffic. And we get to utilize all of our links. So this is a good thing. I want to talk a little bit about that GIPO address. So Remember, when we were flooding our unknown unicast traffic over the ACI fabric, I said, hey, look at this. There's this multicast address. What is this? So every bridge domain will get its own multicast address. So notice down there, we have that multicast address. And we can see it's 225.122.208 for bridge domain 1. Now, each bridge domain, it doesn't get just one address. It actually gets a /28, a range of multicast addresses. And that /28 gives us 4 bits. And what we'll do is we will actually, when we send the multicast traffic over the ACI fabric, so again, it's unknown unicast traffic on the inside, the inner frame. On the outer header, it's going to be multicast. So what we'll encode in the multicast address is the F tag we're going to use when we're sending traffic over the ACI fabric. So let's look at an example here. And this is our multicast address, ends in .208. And let's say here that leaf 1 wants to send unknown unicast traffic over the ACI fabric. So it doesn't know where the destination is. What it's going to do is pick one of those 12 F tag trees. Let's say it picks tree 1, F tag tree 1. When it adds the outer header, that GIPO, the destination IP address, what it's going to do is it is going to use the first bit and set it as active. So it's going to use the first available IP in that /28 range. So when it sends it over the tree, it sends it out one of the links. It's going to send it to .209. So that represents bridge domain 1, F tag 1. If this leaf wanted to send it over F tag 2, it's going to take the second available IP, .210, and send that traffic over tree 2. So it's kind of cool how that works. That traffic, that multicast address, represents flooding, in this example, unknown unicast flooding over the ACI fabric for the bridge domain, but it also represents it for a certain F tag tree. The other thing I want to talk about is ARP flooding. So we talked about unknown unicast. You can turn ARP flooding off. Now, the way we can get this done, we don't have to flood ARP traffic in ACI. The way this is done is if we look at this example, let's say that this server right here wants to send an ARP broadcast to this server. So it's going to say, hey, 10.1.3.12, what's your MAC address? Well, if I send the ARP broadcast, Leaf 101 is going to receive it. And imagine Leaf 101 knows this IP address is behind Leaf 102. So it previously had a device locally attached to it, and that device had an active conversation. So Leaf 101 knows where that IP address resides. So because we're turning ARP flooding off, Leaf 101 doesn't have to flood the traffic over the ACI fabric. It's going to take that ARP broadcast, send it to Leaf 102 directly. So because we learn IP addresses in ACI, that's an awesome benefit. We don't have to flood ARP traffic. So let's go ahead and go over some examples. So let's say that we have server A behind Leaf 101, server B behind Leaf 102, and server C is just another server that's on the bridge domain. And let's say server A wants to send an ARP broadcast for server B. So it does that in step 1. Leaf 101 is going to receive that ARP broadcast. And again, if you look at the ARP broadcast in the wire, it's essentially going to say, hey, 192.168.10.2, what's your MAC address? So what Leaf 101 will do is it's going to look at the IP in the ARP broadcast, and we'll look at its endpoint table. And so what it will say is, oh, okay, I know where that IP is. So let's assume Leaf 101 knows this IP is behind Leaf 102. Well, Leaf 101 doesn't have to flood the traffic. Instead, it can take the ARP broadcast and send it directly to Leaf 102. Now, I don't have this in these pictures, but what it would look like is you'd see the ARP broadcast. That would be the inner frame. And then we would have that outer header. The outer header would be destined to Leaf 102's TEP IP. So we would route that encapsulated ARP traffic to leaf 102. Leaf 102 is going to decap it. It's going to look at the ARP broadcast and say, oh, I know where this IP is. It's locally attached to me. And we'll send that ARP broadcast to server B. Server B will receive it, and notice the other server, server C or leaf 103, they don't get a copy of that ARP broadcast because we're not flooding it. We're sending it directly to leaf 102. Another example is, what if leaf 101 doesn't know where server B is this time? This is a little different. So in this example, server A sends an ARP broadcast for server B. Leaf 101 doesn't know where server B's IP is. So what do you think leaf 101 might do in this situation? It's going to send it up to the spines, just like unknown unicast. So the leaf's going to punt it up to one of the spines. The spine's going to look at its COOP database. It's going to send it to the anycast IPs of the spines. The spines are going to look at their COOP database and say, hey, 192.168.2, which leaf switch is that behind? In their COOP database, it's going to point them to leaf 102. So what one of the spines will do is, remember in the outer header, they changed the destination IP to the TEP IP of leaf 102. We route it to leaf 102, and then leaf 102 will decap the outer header, looks at the ARP broadcast, looks at the IP and says, oh, this IP is behind this locally attached interface. Server B gets the ARP broadcast. Other servers on the bridge domain will not see the ARP broadcast. So big benefit. I'm not going to do a packet walk for ARP flooding. So remember, you can turn ARP flooding on. It's similar to the packet walks when we covered unknown unicast flooding. So for ARP broadcast, we're going to use that same concept of F tags and bridge domain multicast addresses, those GIPO addresses. All right, that's all I got.